Okay, so hello everyone, it's nice to meet you once again. So there are not many of us yet, but still let's start. We're 1 minute late even. So last time, let me remind you, we were talking, first of all, please, someone tell me, the lecturer didn't post the notes on Wiki, but what was the topic of the last lecture? He started vector spaces?
Yeah, we have.
Yeah. Okay, I see. So we will be late then, because today I will not start vector spaces for sure. I'm sorry, that's life, but I'm quite sure that we will catch up later, because he's going to go through many technical details about vector spaces, and there will be not so many problems. But complex numbers have lots of problems, and we really need to make sure that everyone understands everything. So last time in the end, we started talking about roots and we didn't finish. So first, I want to start with a simple exercise of finding some root. So here we have some number and we want to find its 10th root. So I remind you that the complex root is not a number, but it is a set of numbers. Okay. So last time we solved an equation of this form. Today, equation looks like this, where there is some given number, maybe not Z, let me name it W or something. So now it is not 1, but something else. Still, the idea is the same. If this equals this, then automatically, if Z is R1 times cosine of phi1 plus I sine. Let me name it not phi1, but somehow else. Let it be phi. And if W equals R2 times, I don't know, cosine of, I don't know, alpha plus I sine of alpha, then from this, it automatically follows, again, Zn equals W, it automatically follows that R1 to nth power is R2, and n times phi is alpha modulo 2 pi k. Because if two angles have the same cosine and sine, they might be not equal. So this is obviously equivalent to the following. R1 equals nth root of R2, where this root is the arithmetic root, the usual root we already kind of know and can use. And this, well, I can divide by phi. So I obtain this general formula where I remind you it is logical to consider only k from 0 to n minus 1, because after this, it's easy to see that the values will repeat. So this is the general formula. We always, for any complex number w, to find the roots for any non-zero complex number w, because 0 doesn't have a trigonometric form, but for any non-zero w, we can find the root from the absolute value, and we can we can divide the argument by n. So the general formula looks as follows. Okay, here is the same, obviously, thing that in the cosine. I will not repeat it twice. So that's it. Once again, I remind you, this is the complex root, this is the arithmetic root. They are not the same, they just have the same symbol. So applying this to this simple problem, let's go. Let's try to apply it. So I need to find the absolute value. Well, the absolute value of the product is the product of absolute values. That's life. So we need to find the absolute value of this bracket, because for this number, it is simply this number itself. So for this bracket, we already kind of know that we get 2, right? 1 plus 3 is 4, square root of 4 is 2. So this number by 2 is 1024, which, well, lucky for us, admits the 10th power root. This helps to write a simple and beautiful answer, but likewise, so for the angle, we need to know the argument of this. So if I draw this number 1 minus I square root of 3, then it looks like this. So this argument, Majuga uses arguments from 0 to 2 pi, right? So the argument should be this angle. But for simplicity, it is simpler in this problem, as I already said. In problems, I will use different values of angles depending on how nice they are for computation. So let me use this angle. It is minus pi over 3. So minus pi over 3 plus 2 pi k divided by 10. Any questions at this point? So the first part is simply 2. I hope everyone knows this number by heart. That's 2 to the 10th power, a very useful number. And we are not going to use it in algebra, but in other courses, it's going to be useful. So, and here we have cosine of minus pi over 30 plus pi k over 5, and the same sign. It's not important to go from this representation to this, so we could leave it like this, it doesn't matter. It depends, well, kind of on your viewpoint, which is simpler. I don't really know, but still, this is the idea. So before we move on, I have one more question. How does this answer look like? What happens if I take those roots and draw them on a plane? Let me, well, it will be hard to draw them precisely, but let me draw a like an approximate picture that kind of explains what is happening. So if I take k equals 0, then I have something with the angle minus pi over 30. So it is very close to the real line, but somewhere in the negative direction, somewhere here. Okay, this is again an approximate picture. I'm not going to find exactly the angle pi over 30. And the length is 2. So I have a vector like this with length 2. Then the next one also has length 2, but the angle is pi over 5, that is 6 pi over 30, minus 1 pi over 30, that is 5 pi over 30. So it is pi over 6. A nice angle, in fact, but that's a coincidence. I didn't really try to make them so. The next one has some, again, some random angle, some 11 pi over 30 or something. The next one, etc. So they look kind of like this. All of them have length 2. And all those angles between the previous and the next are pi over 5. So they are all equal. Thus, we can say something about the ends of the vectors. What can we say about the ends? Ends. I don't know why I pronounced it. What kind of figure is this?
A circle?
Not really. A circle has infinitely many points, but here we have 10 points. What do they form?
How to say it? Yeah.
Aha, we don't know the English for this. Okay.
Yes.
I see. It is a regular tengon. Well, one can say decagon, or one can say simply tengon. I think that's not a mistake. Okay. So правильный десятиугольник. Regular means правильный. So because again, all those angles, each of them is pi over 5, so they're all equal. So all such triangles are equal, etc., etc. So this is the general behavior of roots. Usually, when you take root of some number, then you have many roots. If you take the root of nth power, you get n roots, and if you examine this formula, you can easily see that they always form a regular n-gon. If you take third power roots, you get a triangle, a regular triangle. If you take fourth power, you get a square, etc. If you take roots of second power, then you get a two-gon, which is a pair of opposite vectors, plus minus something, which coincides with what we already know about square roots of usual numbers. So a square root, again, is for us a pair of two roots, plus minus something, together. Okay, any questions about all this entire topic? Otherwise, I shall move forwards. Okay, so I have copied a problem. So about roots, we have kind of talked about all the main things, but still, let me pose two more problems so that we see some nuances. So this problem says that there is a well-known property of roots for real numbers. Like when we were talking about multiplication or like powers or addition or whatever, we were saying that all the properties you know for real numbers also work for complex numbers. However, roots are more delicate, more hard. I'm sorry. So it is not obvious whether every property works for them or not. And in fact, not all properties work. So it is very important to understand which one do and which one don't, which ones don't. So any ideas about this?
It doesn't, I think, because in cosine we will get divided by ns, and in case we just vanish s here.
But here it gets multiplied by s, so it is multiplied by s, then divided by ns. So s kind of.
Is it possible to divide s on ns?
Yes. You get 1 over n.
That's all? No?
If
Maybe.
s is odd, then and z is negative.
Negative?
Then
Complex numbers can't be positive or negative. They're just like they are. Well, how many numbers are there in this set? I remind you, this is not a number, but a set of numbers.
From 1 to ns minus 1.
From 0 to ns minus 1. So
0.
there are ns numbers. This is a simple rule. If you have a root of some power, this is exactly the number of possible roots. And this set has n numbers. So it is obvious they can't be the same set. Those things can be equal as sets. They have different number of objects inside. It's not possible. And indeed, this was a trick when you said about S and NS. I interrupted you so that, well, you get confused. But in fact, if you write the formula, then in the cosine, you will have something like phi plus 2 pi k over ns. So it will be like s phi plus 2 pi k over ns in one formula and phi plus 2 pi k over n in another. So in this part, s cancels. But in this part, it does not. So those two things don't provide the same series. They this one has more details, more results. Okay. Any questions for this problem? Someone is writing in chat, but it's hard for me to read. Okay, give me a second. One more time about sets. So once again, a complex root of a number is a set of possible results, not one result, but many of them. It is like not a function, but a multifunction. Unfortunately, we would prefer if we could pick some one particular root and say it is the best, but there is no such way, unfortunately. So this is a set of different ns numbers. One number, another, many numbers. And this is a set of n numbers. So, well, those sets have different number of objects inside. They are not the same. Okay, so then let me finally solve one. Okay, I'm sorry, I shouldn't. Okay, I'm sorry, this is not the problem, but also part of solution. I'm sorry. The problem is, let me find this cosine. This cosine is an interesting thing. Well, like some of you might know how to find it using geometry. This angle is related to the regular pentagon. So maybe some of you know how to find the cosine of this angle, like it is 72 degrees or something, but it is not easy. Not easy. There are some complicated ways to do it using trigonometry, but again, they're not easy. They use some tricks inside. And in fact, those tricks are inspired by complex numbers. If you don't know complex numbers, it is hard to invent such tricks. So today we're going to find this using complex numbers. The idea is as follows. This number is this number plus this number. Well, and divided by 2. Okay, this plus this gives us 2 cosines. That's not a huge problem because I can simply divide by 2. So this number separately had no relationship with complex numbers, but those two numbers now they look more, well, complex, and they are very interesting complex numbers that have meaning. They are in trigonometric form already. So I can use some intuition about them. So let me denote this number as Z. Then I claim that this number is Z inverse. Please look at this. Indeed, on one hand, if I multiply them, I get difference of squares. I squared turns the minus into plus, so I get cosine squared plus sine squared. On another hand, I can say that this is, we remember that this minus we can turn into plus by putting minus inside. This is something with argument minus 2 pi over 5. So when you multiply those two numbers, 2 pi over 5 gets cancelled with minus 2 pi over 5, you get 0. So those two numbers are indeed inverse. So very good. Also, this number is Z, well, conjugate, but that's not important right now. What is more important for me is that it is Z inverse. For this particular number Z, those two things are equal. They're not always equal, but sometimes. So my goal is now to find Z plus Z inverse. What do we know about Z? We know that Z to the 5th power is 1. Look, if you raise this number to the 5th power, then this 5 disappears and you get cosine of 2 pi, that's 1, and sine of 2 pi, that's 0. So I know that Z to the 5th power is 1. I want to find Z plus Z inverse. Well, let's work with this polynomial. I hope you know that 1 is the root of this equation. So I can divide this Z5 minus 1 by Z minus 1. I will not perform the division right now in details. We are going to talk about division of polynomials in just a few minutes. But right now, let me simply provide the result. So if I put 1 to the left-hand side and split this into 2 brackets, the first one is Z minus 1, the second one is like this. And the second one doesn't look nice, but still, as my number Z doesn't equal 1, look at it. It is not 1, right? Cosine of 2 pi over 5. I don't know what it equals to, but certainly not 1. Okay. So as Z doesn't equal to 1, I can simplify my expression. Now I have not the equation not of 5th power, but of 4th power. It looks less nice, but still it is of 4th power. Well, it's not much better. We don't know how to solve equations of 4th power. Okay, no one does. No one does. But this particular equation is kind of symmetric in its form, and there is an easy trick. We can divide this expression by Z, as Z is non-zero. Again, looking at this number, we can see it is not 0. Then we get the following. We're very close. Now, let W be Z plus 1 over Z. Then we have the following. This plus W plus 1 equals 0. If we somehow express this through W, we win. Well, I claim we can. Indeed, W squared is Z squared plus 2Z times 1 over Z plus 1 over Z squared. That is Z squared plus 1 over Z squared plus 2. Here Z cancels. This means that I can pass from this to the following. W squared minus 2 plus W plus 1 equals 0, which means that this is the quadratic equation for W. My goal was to find W, and I have a quadratic equation for it. We can solve it. Any questions at this moment? Let me make a pause before I solve it.
Isn't equal 1.
What?
Why Z isn't equal 1?
Well, because again, we are not looking for the root 1. We know it exists, but that's not the root we're looking for. Z equals this. But 2 pi over 5 is not 0, is not 2 pi k. And this angle is not 0. this kind of 1 has 5 roots of 5th power. They form the regular pentagon like this. So this one is 1 and this one is Z. I'm trying to find Z.
Okay.
Well, I'm not really trying to find Z. I'm trying to find Z plus 1 over Z. This one is 1 over Z. I'm trying to find their sum. So again, for this sum, I have obtained a quadratic equation. Any other questions about how I obtained?
Can you explain these few steps again, please?
What?
Can you explain? Можете несколько последних вот этих вот шагов?
Несколько это сколько?
Ну вот последние 4 строчки.
Okay, so I introduce. So to simplify this expression, I introduce the variable w. I let w to be z plus 1 over z. Then this plus this goes into this w. This one is still here, and this z squared plus 1 over z squared is still here. But I don't like this. Now it's worse. Now it contains both z and w. So I want to somehow, this part, to somehow represent through w. So lucky for me, w squared equals this, then this equals w squared minus 2. I can put this 2 to the left-hand side. Again, it is hard to understand how I guessed to consider this w, well, because I'm trying to find it, but still it's not really obvious, and how I guessed to consider w squared. But again, this problem is kind of more a showcase, okay? It is not like a problem that has thousands of variants and you need to be able to solve each of them. So don't worry if it is not obvious why I guessed to consider this, but please understand what is the result of this, what this trick allowed me to do. So now I get a quadratic equation. I can write the discriminant. And I can write w equals -1 plus minus square root of 5 over 2. And that's it. I have found my cosine, almost. I have two values, but cosine of 2 pi over 5 is greater than 0. This angle is, well, somewhere in the first quadrant. Thus, it equals -1 plus square root of 5 over 4. Why over 4? Because w was twice the cosine, right? If you return to the beginning, please look, cosine equals 1/2 of z plus z inverse. Okay. So let me make a change. Okay. So that's it. I have found w, I have found my cosine. Very interesting expression for the cosine. It doesn't look like something we are, well, we know well. So it doesn't look similar to other cosines and sines we know, but still we can find it. This is again an illustration to the power of complex numbers. Using them, we were able to solve a problem that the problem itself didn't have any complex numbers inside. The problem was just a regular problem. But somehow, complex numbers are very useful in it. That's just one of many, many, many situations where this happens.
Sorry, can I have a question?
Mhm.
Why in our answer we have division by 4 if in W we have division by 2?
Okay, let me repeat once again. So cosine of 2 pi over 5 is 1/2 of this plus this.
That is why we divide on 2.
Yeah,
Okay.
yeah. When we add this to this, then the imaginary part cancels, but the real part gets doubled. So I need to divide.
And can I have one more question, please? I didn't get why z in the power of 5 equals 1.
Well, if you look at z, if you raise it to 5th power, the arguments gets multiplied by 5.
And cosinus 2 pi equals 1. Yeah.
Cosine of 2 pi equals 1. And sine of 2 pi equals 0.
Thank you.
Okay. Unfortunately, this trick kind of works only for this angle, so it's not something that is widely used. Because, well, if your angle is like something over 3 or over 4 or over 6, you already know how to find it. It is well known. And if it is like over 7, for example, then you will get an equation of high power. Then here you will get 7th power, here you will get 6th power, and you will be able to do something similar to those steps, but here you will obtain not a quadratic equation, but a cubic equation, and cubic equations are hard. So for 7, it kinda can be used, but not really. And if your denominator is higher than 7, say 11, there are reasons why it makes sense to use prime numbers. If it is 11, then you are stuck. You will get here an enormous power, 5th power, and equations of 5th power, no chance. So unfortunately, this trick is kind of good for demonstration, but not really helpful in other situations. Okay, still, I hope I kind of showed some power of complex numbers. And now my goal is to move to the next topic to discuss polynomials. So first, let me talk about division with remainder. That's a topic that was on the lecture and that many of you maybe know from school or somewhere, but we suppose in our course that maybe some of you don't. So let me provide brief explanations on this process. So you should know from the lecture that if you have a polynomial over any field, that means with coefficients from any field, and another polynomial over the same field, then it is possible to find such polynomials Q and R. They are called quotient, частное, and remainder, остаток, that are very similar to the process of division with remainder that you know from discrete mathematics. First, such that first this holds, and second, this R is kind of smaller than what we divide by. But for polynomials, there is no such thing as smaller, but there is such a thing as degree. Degree of R needs to be less than degree of G. Then we say that R is a remainder. And there was a powerful theorem that we always can divide with remainder, and such a process is unique. There is only one possible way to divide with remainder. And existence follows just from the fact that we know how to. We have an algorithm. So let me present this algorithm in this example. The algorithm goes as follows. You take your polynomial f and you take your polynomial g, and you consider their highest powers, their main terms, their highest terms. In the end of the year in algebra course, we will talk about highest terms in more details for polynomials with several variables. But today the polynomials have only one variable inside, so that's easier. It is intuitively obvious what is the highest term. So now I divide this monomial by this monomial. Monomial одночлен. the result is 2x squared, right? 2x to the 4th power divided by x squared. That's 2x squared. Then, like I do in the usual long division, that's the English name for деление уголком. They call it long division for some reason. Well, for some reason, because it's kind of long. So the same way I take this result and multiply it by the whole g, by the whole thing we are dividing by. The result,
It's Bezout's theorem, yes?
no.
Okay.
Bezout's theorem is that if you have a root, then the polynomial is divisible by x minus something. So if I multiply this by this, I get 2x fourth, 6x cubed, and 2x squared. Now I can subtract again the way we do it when we're performing the usual division of numbers. Minus 3 minus 6 gets 3x cubed, 4 minus 2 gets 2x squared, and this part I rewrite. Sometimes people omit part of this, kind of rewrite, for example, only minus 5x, but omit plus 6, saying, I will rewrite it later on next steps. But I don't recommend this. It is an easy way to make mistakes. So my next step is to find the main part, the highest term here and here. Well, here it doesn't change. It is still the same term. Nothing changes. But here, well, it is now 3x cubed. So again, I divide 3x cubed by x squared. The result is 3x. Okay? 3x cubed by x squared. 3x. So now I take 3x and multiply by this whole expression once again. I get 3x cubed minus 9x squared plus 3x. And I subtract. The main term cancels, that was the goal. And the next term becomes 11x squared. The next one is minus 8x, minus 5, and minus 3 more, and plus 6. So my final step, I once again consider the highest term, consider here the highest term, divide one by another, I get 11. So I multiply 11 by this entire expression, I get 11x squared minus 33x plus 11, and subtract minus 8 but plus 33 is 25. 6 minus 11 is minus 5. So I claim we have the result. So this is the quotient, and this is the remainder. Now, my remainder, I can't divide it anymore because its highest term has smaller degree than x squared. I can't divide 25x by x squared. I won't get a polynomial, I will get a fraction. So I stop. That's it. Any questions? This procedure is kind of easy, but it is a stepping stone in many algorithms. We will need it, okay, in some situations. That's why I'm talking about it. Okay. Are you sure there are no questions? I will move to the next topic then. Okay. So next problem uses Bezout's theorem someone wanted to talk about. So it is not a problem, it's two problems. Two problems is twice as good as one problem. So I have some polynomials. Let me start with the simpler one, this one. And I want to split it into linear factors. What does it mean? Factors, I remind you, means множители. Разложить на линейный множитель. What does it mean? It means to represent it in the following way. Well, let me maybe write z to the 4th power plus 4, because for complex numbers, it is customary to use the letter z. So I want to represent it as a product of 4 factors, and each of them will be linear, first degree polynomial. Why do I write them as, well, why 4 factors? Because the power is 4. So if each of the degrees is 1, then there need to be 4 of them so that the total degree is 4. That's obvious. So how to find those factors? Well, Bezout's theorem tells us that we need to find roots. We need to find the roots of this equation. Find roots of this equation. But this equation is easy to solve. Generally, we don't know how to solve equations of 4th power, but you won't have such a task. This particular equation, we know how to solve. We need to put -4 to this side, and then we already know the formula for 4th power roots. So Z equals 4th power root of 4, which is the usual root, the arithmetic root, times cosine of what? So this is 4 times cosine of pi plus I sine of pi. So here I get pi plus 2 pi k over 4 plus I sine of pi plus 2 pi k over 4. I want to write particular numbers, so let me write all the possible variants. So this becomes square root of 2, right? This is again the usual root, so we can apply everything we know from school. This is square root of 2. And this is cosine of pi over 4 for k equals 0. What is cosine of pi over 4? That's 1 over square root of 2 plus I 1 over square root of 2, right? Then for the next angle, the cosine becomes negative. For the next angle, they both become negative. And for the next angle, the first one becomes positive. Geometrically, it looks like a square. This point, this point, this point, and this point, right? This angle is pi over 4. So, well, I can cancel square root of 2. The problem was invented so that it cancels. So I get those 4 values. So z to the 4th power plus 4 equals z minus 1 minus I times z plus 1 minus I times z plus 1 plus I times z minus 1 plus I. And if you take time and multiply all those 4 brackets, you will indeed see that everything cancels and you get the expression in the left-hand side. But I don't recommend spending time like this. Any questions right now?
How did you obtain 1 over square root of 2?
Well, that's cosine of pi over 4. I know it from the table of cosine. That's you might know it as square root of 2 over 2. Okay.
Ah, okay.
That's the same. You write it like this or like this, depending on the situation. In this situation, this looks nicer because it is more obvious that everything cancels.
And where we write, where we add 2pk.
Well, again, I'm sorry, I did it like in my head, but this corresponds to pi over. Let me take. This is cosine and sine for pi over 4. This is for 3 pi over 4. I add 2 pi to the nominator. This is for 5 pi over 4, and this is for 7 pi over 4. Those again, the pi over 4 is this angle, 3 pi over 4 is this angle, etc. So they kind of have the same cosines and sines, but with different signs. English is hard.
Okay.
Mhm. Okay, let me try to solve one more problem of the same kind. How much time do we have? 30 minutes, 35 minutes even. That's wonderful. So the next problem asks about this polynomial. And again, this equation is very simple also, so everything is going to be the same way, but the result is kind of interesting, so I want to show it. So once again, I wish to take roots of 6 power. So I get pi plus 2 pi k divided by 6. So I want to write down all the possible results. So let's be careful. The first one, cosine of pi over 6. What is this? Pi over 6, the small angle, cosine, so the bigger side. So that's square root of 3 over 2 plus I 1 over 2. Okay. Let me draw a picture for this. Pi over 6.
Sorry, how do you obtain cosine p plus 2pk divided by 6?
Well, this is 27 times cosine of pi plus I sine of pi. Minus 1.
Oh, well, okay, thank you.
So the same, I just didn't want to repeat it because it was in the previous problem the same way. So this is the first value. Now the next value. If I add 2 pi here, then I get 3 pi over 6. 3 pi over 6 equals pi over 2. So cosine is 0 and sine is 1 minus 1. So that's simply I. Okay. For the next one, 5 pi over 6. Unfortunately, well, we can't really cancel or something. So we need to find out what is this, what are the cosine and sine of this angle. Well, it is pi minus this angle. So it has the same sine, but the opposite cosine, like this. Okay, everyone still alive? So the next one is 7 pi over 6. And I will not describe in details why I think so, but the values will be like this. Again, you can think about this angle, about which quadrant, etc., and apply some formulas from school mathematics, and you will get it. Now, now my pen stops working. Okay. Now 9 pi over 6 is 3 pi over 2. So once again, I get some good angle. In fact, that's 0 minus I. And the sixth one, finally, once again, let me simply write the result without much explaining. It's going to be this. So those are 6 variants. So z to the 6th power plus 27 equals z minus 1/2 minus I square root of 3 over 2 times z minus square root of 3i times z minus, no, plus, wait, not 1 over 2, 3 over 2. Okay, square root of 3 times square root of 3 is 3. So plus 3 over 2 minus I square root of 3 over 2 times z plus 3 over 2 plus I square root of 3 over 2 times z plus square root of 3I times z minus 3 over 2 plus square root of 3 over 2I. Those 6 brackets. I'm sorry for writing them on 3 lines, but this product. Okay. Now let me enhance this problem by considering the next problem. Let me take the same polynomial and it doesn't work, and split it into factors without any I. Okay, complex numbers for this problem are a tool, but not the goal. We have some polynomial with real coefficients. I want to split it into brackets which have also real coefficients. I claim it is very hard to do so. You can split into 2 brackets if you know the rule about sum of cubes, but it will be hard to progress from this point to somehow split further. But using this expression, it is very easy. Who understands how to do this? It was in the lecture. Aha, it was long ago in the lecture. Okay, so those roots, they look like this. They form a regular hexagon, but that's not very important right now. What is important is that they split into pairs of conjugate roots. There is a special theorem that says that if the original polynomial has real coefficients, then all the roots split into such pairs. And so I can pick pairs of brackets in this expression. This and this one, this and this one, they have the same real part, but different complex part. And finally, this and this, they have the same real part, but different complex part. I claim I can multiply each pair by each other. For the first pair, I get this multiplied by this gives me z squared minus square root of 3I squared. This is the difference of squares, something with minus and something with plus. Next pair gives me z minus 3 halves squared minus square root of 3 over 2I squared. Okay, please look at this and this bracket. They have z minus 3 halves the same and this part with different signs. So again, it is a difference of squares. If there is some question about this difference of squares, I wish to hear it right now before I continue. No, it's clear? Finally, for this pair, it is z plus 3 over 2 squared minus the same thing. So if I simplify, here I get plus 3, okay? This squared is simply minus 3, and this minus with this minus gives me a plus. The second one gives me z squared minus 3z plus 9/4. This is this square. And plus, this minus gets cancelled with I squared. So plus 3/4. Okay. The final one is the same, but with plus. So altogether, the result is as follows. So the result kind of belongs to school level mathematics, right? I have taken a polynomial and I have expressed this as product of three polynomials, no complex numbers inside. However, it is very hard to obtain this. How would we find those polynomials? This one you can find if you remember again the formula for sum of cubes, but those two, it's very hard to obtain them. Well, you can obtain them if you guess good enough, but guessing is not a real method. So this way, I split a polynomial into quadratic factors over R. Any questions?
Sorry, can you please one more time explain the last task when we have z square minus 3 минус корень 3 в квадрате. Откуда у нас это получилось?
Вот это?
Выше. Z квадрат. Да.
Okay, so here you have those two terms underlined by one red line.
That is why we just have every bracket just in square.
Yeah,
Okay.
this is the difference of squares.
Thank you.
This is the difference of squares, and this is the difference of squares. I pair, so I claim that there is always a way to pair brackets in, well, to couple brackets into pairs, such that each pair, when you multiply them, I disappears. Complex numbers disappear. Yeah?
А задание нужно было сделать, чтобы получились квадраты или что?
Split into linear and quadratic factors over R. Нужно было сделать, чтобы получились линейные или квадратичные множители, как повезет, это зависит от конкретного многочлена. Но чтобы в них коэффициенты были теперь вещественными, не комплексными, чтобы и куда-то пропало.
А и у нас пропало, потому что мы перемножили обратные скобки, да?
Не обратные, а сопряженные скобки.
Сопряженные, да. Спасибо.
Let me do one more exercise of the same type. Okay. It will be harder and I won't finish it. Okay. I will give the idea and then I will like, sorry, it doesn't work. So I will like leave it half done because we don't have too much time. But let me start it. So now I consider the second polynomial here. So, well, now to start doing this task, I have to solve this equation. And now we have a slight problem. It is not of the simple type we already know how to solve. And unfortunately, I can't give you any good method or something to solve such equations. But this particular equation we still can solve if we're like, if we can like smartly guess something. Indeed, you can see that it kind of contains two parts and both parts kind of look good. If you look at the first part, you can guess that it equals x squared times x squared plus 4x plus 4. And this is x plus 2 squared. And I can represent this as a square of this. Okay. But now we can see this is a difference of squares. Complex numbers bring a huge joy for us. Now plus and minus are the same. Plus 1 is minus I squared. So any sum of squares becomes a difference of squares. So let me split everything into two factors. Okay. Now I have two quadratic equations. Let's solve them. Let me now separate the problem into two problems. Part 1, this equals 0. Well, I can write the discriminant. It is 4 plus 4i. And I can write that x equals minus 2 plus minus root of 4 plus 4i. In fact, it is not necessary to write plus minus root because this root is two numbers. I can write plus root divided by 2. It's easy to see that it is the same as minus 1 plus root of 1 plus 1i. Okay. I simply cancel 2 everywhere. So what is this root? Well, 1 plus 1i has argument pi over 4. Thus, when I divide it by 2, I get pi over 8. So unfortunately, it is minus 1 plus cosine of pi over 8 plus I sine of pi over 8, and that's not it. Everything is multiplied by square root of 2 because 1 plus I has also absolute value square root of 2. And the same but with minus. This minus we get if we put here not pi, but if we add 2 pi here. I mean, if we add, like this. Okay. So the fortunate news are that we got two roots. So we can write that this equals x plus 1 minus cosine of pi over 8 minus, I'm sorry, by square root of 2, minus square root of 2 by sine of pi over 8 by I times, and the same expression for the another root. The bad news are that, well, this pair of brackets is not conjugate. Because their, okay, let me write it. Because their real part is also different. Their imaginary part is kind of, well, the same with plus and minus, but their real part is different. So we can't say that those pairs are conjugate. And indeed, if you multiply them together, well, guess what do you get? You get this. Their product does contain complex numbers. If you multiply them backwards, well, complex numbers won't cancel. But if you consider now the second equation I have, then you can do all the same steps. I will skip them. And you will obtain the following result. And then you are able to pair this with this and this with this. And after you multiply each pair, you get a polynomial with real coefficients. They will be not nice. You will get the following, that the original polynomial equals x plus 1 plus cosine of pi over 8 square root of 2 squared plus square root of 2 times sine of pi over 8 squared multiplied by, and the second, well, is kind of like this. So both brackets kind of contain cosines and sines, and they won't go away. So it is kind of not very nice expression, but still it contains no complex numbers. It is an splitting of the original polynomial into two quadratic polynomials. And note that you wouldn't be able to really get it any other way from the original polynomial. Okay, I hope this demonstration was enough.
I have a question. Can you please how you find the angle for this one?
The angle is pi over 8.
Yes.
So 1 plus 1i has angle pi over 4. Okay.
Yes.
Well, when I divide it by 2, I get pi over 8. I have square root.
Yeah, we have square roots, so that's why we add just the square root of 2 after that.
So again, the square root will have angles like this. That is pi over 8 plus pi k. So we have two possible values, pi over 8 or another one which is kind of the same but with a minus before everything.
And why we divided by 2? There's this one.
By 2?
Yeah.
Because it is a square root. Square root is the root of second power. N equals 2.
Yeah, thank you. I got it.
Yeah.
And
Unfortunately,
so then we just multiplying by square root of 2 just to make it just the same. Or why we are multiplying by square root of 2.
Oh, you are right. I don't know if you are intentionally right, but you are right. Not the square root of 2, the fourth power root of 2. Sorry, maybe it wasn't as helpful as I hoped, but 1 plus I equals square root of 2 times cosine of pi over 4 plus I sine of pi over 4. So I need to divide the argument by 2 and take two possible values. And I need to take the square root from this absolute value. So I get fourth power root of 2.
Yeah, okay, I got it now. Thank you.
I'm sorry, I really didn't notice this mistake. Okay, any more questions? That's very good that you are able to find mistakes. Then we don't have much time, but still, let me at least do 4 very quick questions. And there are some interesting questions that I wanted to cover, but well, next time. So next time I will solve one problem about complex numbers and immediately start vector spaces because we are kind of late at that topic. But still we have one more problem. And right now, let me do some quick problems. So this problem asks to find some polynomial as simple as possible, such that it has a double root 1, simple roots 2, 3, and 1 plus I. Simple root means, well, not a multiple root, okay, root of power 1. Well, if such polynomial exists, it should be divisible by z minus 1 squared. That's the definition of a double root. Double root, that is, you know, a joke that double root is when you put it once and you get 0, and you put it a second time and you get again 0. Obviously, that's a joke. No matter how many times you substitute some value into the polynomials, you get the same. But a double root is when there is a bracket like z minus 1 squared in our polynomial. Likewise, 2 is a simple root. It means it has z minus 2 inside. 3 is a simple root. It means z minus 3 is inside. 1 plus I is a simple root. It means it has z minus 1 minus I inside. And also it might have something else. but the smallest possible degree means that from this huge set of different polynomials for different g, I get different values, different polynomials, but the smallest of them is to simply take this, to do nothing else. This is the answer. Questions? Okay, then let me consider the same problem for the same polynomial, but over real numbers. I want to have a polynomial that won't have any I inside of the smallest possible degree. Then this one doesn't suffice. This one has I. Well, if f of z is such a, let me write f of x, a polynomial, then 1 minus I is also a root. There is a powerful theorem, right? If some number, if some complex number is a root of a polynomial with real coefficients, then it should have a pair. I can draw a picture like this. It has a double root 1, roots 2, 3, 1 plus I, and so 1 plus I should have a pair, 1 minus I. Those roots don't require a pair because they're on this axis. Okay, they're paired to it themselves. But those roots require a pair. Otherwise, complex numbers won't cancel. So this means that f of x needs to be x minus 1 squared by x minus 2 by x minus 3 by x minus 1 minus I by x minus 1 plus I by some g of x. And again, the smallest possible is, well, simply this one without any g. I can simplify this part, canceling the imaginary part by writing it like this. Okay. Any questions? Then let me quickly do the same problem.
Can I have a question about the previous task, 27.3a? How did you find smallest possible degree?
Well, again, so all possible such f look like this. So their degree is 2 plus 1 plus 1 plus 1, that's 5, plus the degree of g. Well, this means that for this degree to be the smallest possible, g has to have the smallest possible degree. Well, let's have g equals 1, the constant, the polynomial of 0th degree.
So we just we write it the same, but without g because g equals 1. Okay, thank you.
Yeah. This is the set of all polynomials that have those roots that are described above. And this is the simplest among them. So let me have the same problem for another set of roots. Now we have a double root I and a simple root minus 1 minus I. There is not much difference in this exercise, but still let me do it quickly so to show how it works. So then for the first task, we get that I needs to be, well, a double root, and minus 1 minus I needs to be a simple root. So that's it. again, if I look for all such polynomials, I can write times g of z. And if I look for the smallest one, then it's simply this. Nothing really needs to be proved or something. It's obvious. And for 4b, if I is a double root, then I conjugate, that is minus I, is also a double root. Not only each root needs to have a pair, but those pairs need to have the same multiplicity. And similarly, if minus 1 minus I is a simple root, then minus 1 plus I is also. So my polynomial needs to be like this: x minus I squared times x plus I squared times x plus 1 plus I times x plus 1 minus I. That is x plus squared plus 1 squared times x squared plus 2x plus 2. Questions? This problem is easy to solve because I use a powerful theorem from the lectures. Obviously, if I were somehow explaining this by hand, it would be very hard. But when I use the theorem that roots go in pairs, it's a very simple process. Okay. Are you sure there are no questions now? Well, then let us stop at this moment. We will have, as I said, one more problem, but it won't fit into 1 minute. So let me do it the next time. And then we will go to vector spaces, and that's a journey for the most part of the remaining year.
Sorry, can I have a question?
Mm-hmm.
Not about, okay, also about this task. Can you explain why if I is a double root, then not I equals minus I?
First of all, that's not I, that's I conjugate.
I conjugate, yes.
Сопряженное к числу I. Second, again, this is a theorem from the lecture. Please consider the lecture notes. You might know that there is an oral test soon, even on theorems, etc. Well, it's hard to progress without knowing theorems. Well, there is a powerful theorem that if a polynomial has only real coefficients, then all its roots go in pairs of conjugate roots, symmetric with respect to the real line.
Okay. And can I have also one more question about the first task? I just didn't get how we came from 512 to 1024.
Oh, that was far ago.
It was the first task.
So I divided, so I said that for this thing in brackets, we already know from the previous time that its absolute value is 2.
So that is why we just multiply. Okay.
So I take it outside. So this by 2 is this number. Yeah.
Okay, no questions. Thank you.
Okay, that's not very hard. Okay. Any more questions? Anyone?
Sorry, can you explain how we get just angle just in usual case, just in time?
I'm sorry. I don't.
Just we get the angle like for the roots, like just how do you say, how we obtain it?
Yeah, good. I don't understand. You mean how to find roots?
Yes, just in the trigonometric form.
Yes. So again, there is a the simple rule that is described in this line let me so to find nth roots of a complex number, I take the nth root of its absolute value separately. That's easy. And for the angles, I take the angle of my complex number. I add 2 pi k for different values of k, like this, 1, 0, 1, 2, etc. And I divide it by n. It is easier not to remember this formula, but to understand how we get it, because this proof is very easy. But of course, theoretically, you can simply memorize the formula. The idea is that this angle needs to be some angle that when you multiply it backwards by n, you get the original angle. That's obvious. Because raising backwards to nth power by de Moivre's formula means multiplying the angle by n. Okay.
Yeah, I suppose. Yeah, just I need to think
Okay,
about
if you maybe you need to think a bit about it, and if you have more questions later, do write me when you're doing the homework. In particular, there are obviously going to be questions about roots today. So, anything else? Then I suggest stopping at this point. Once again, it was, I hope, quite good this time, and next time we start vector spaces. Meet you in a week.
Okay, thank you. Goodbye.
Bye.
Bye.
Goodbye.